Finally, we get to talk about calculus with several variables. Let's take a look at some pictures and see if we can get some intuition on what we'll be doing. So in Calc 1, we found the tangent to the curve at a point. The tangent was a line, our curve was one-dimensional, and so we found the tangent at that point using the derivative. We want to develop the same sort of thing, but for 3 space. So here's a nice average Joe surface in 3 space. Now, I can come up with a tangent line to this, but there are infinitely many tangent lines to that spot. The one thing all these lines will have in common is they will be in the same plane. So what we're actually looking for is the plane tangent at that point. So how do we do this? Well, first off, let's look at some planes that cut into it. If I let x equals 3, this is the plane parallel to the YZ plane. You can see it cuts a parabola in the surface, or it cuts a curve in the surface, and I can use normal calculus, one-dimensional calculus, to figure out the tangent line at that point. There's a line tangent to the curve at that point in the plane x equals 3. Okay, cool. Now we want another one. We need two lines determine a plane. So let's clean that up a little bit. Now I want to try y equals 3. So there's my point A. I can come up with the line going through the point in that plane, tangent at that point on the curve. And now ignoring the planes, I have 2 lines, and you can see how the 2 lines will form a plane. So now all I'll need to do is come up with the equation for that plane. That's not the equation, that's just the plane. Now let's figure out how we actually do all that. So partial derivative. To find the slopes, we need to find derivatives in the directions with respect to x and the direct with respect to y. So these should look fairly familiar. The partial with respect to x is the limit as h goes to 0 of f of x plus h comma y minus f of xy all over h. Similarly, the partial with respect to y of xy is the limit as h goes to 0 of f of x comma y plus h minus f of xy all over h. Now don't worry, I won't make you do these by hand. The things you want to remember when you are taking the derivative with respect to x, everything but x gets treated as a constant, including the y. If you're taking the derivative with respect to y, everything but y is treated like a constant. Let's look at an example. Here's the equation for the surface we played with a minute ago, and there's a quick graph of it. So if I take the partial of this with respect to x, notice there's not much to go on. I've got a 10, that's gone. I have negative x minus 2 squared, so that becomes the 2x minus 2 to 1 less power. And the crap with the y, that goes away. So the partial with respect to x is just negative 2 times x minus 2. The partial with y is going to look the same, except with a y. So this one's straightforward. This one's a little easy. Let's try a more interesting one. Suppose we have x squared y minus 3y to the 4th. I'm going to take the derivative with respect to x. So notice this part's going to go away because it has no x in it. So all we have to deal with is that first part, x squared y. So the derivative of x squared is 2x, and the y is just a constant, gets dragged along for the ride. When I take the derivative with respect to y, I have to deal with both terms because they both have y's in it. The first one, I have something times y, so that x squared is just a constant out front. And then I have minus 3y to the 4th. That's going to become 12y cubed. Let's try a more interesting one. Suppose I have y e to the 2x over x plus y squared. Now all of your rules from before work here as well. Product rule, chain rule, quotient rule, sum rule. We're going to get into some weird chain rules, but right now we're going to stick to normal chain rule. So nothing funky yet. So if I'm taking the derivative with respect to x, these are the only 2 things that have x's in them. So let's see what we get. The bottom, x plus y squared. Derivative of the top, well, y is just a constant, so it gets dragged along for the ride. So the derivative of the top is y e to the 2x times 2 because of the chain rule, minus the top times the derivative of the bottom. The only x's on the bottom is a single x, so it's derivative of 1, all over the bottom squared. Now let's take the derivative with respect to y. Here we have y on top and y on bottom. Let's see what we get. I have the bottom times derivative of the top. This time the derivative of the top is e to the 2x because that's treated as a constant. Minus the top times the derivative of the bottom. I've got a y squared in the bottom, so the derivative of that is 2y. all over the bottom squared. Now that we know how to find partial derivatives, we need to figure out how to find the equation for a plane. Suppose I want a plane going through the point x0, y0, z0. We've already seen planes. Anything that's linear, where the variables of x, y, and z are linear, is going to be a plane. Like your y equals mx plus b for lines, you have something similar for planes. This would be the equation for a plane. Some constant x minus the x coordinate, some constant y minus the y coordinate, some constant z minus the z coordinate equals 0. This is called a standard form. And you probably don't see it much with lines because it's a stupid way of writing it. So what I really want to do is see what's going on here. I'm going to solve for z. So I've got z minus z0. That z0 is going to go at the end in a second. So I've got something times x minus x0, something times y minus y0. Just like with the slope-intercept form, that a and b is going to give you the slope in terms of x and the slope in terms of y. So that's where these partials are coming into play. So the equation of our plane at the point x0, y0, z0 is given below. So remember this one? X squared y minus 3y to the fourth. We already came up with the two partials. Here's a nice picture of that function. Let's say I want to find the equation for the plane at the point 2, -1, -7. The partial with respect to x at that point is -4. The partial with respect to y at that point is 16. Plugging that into our equation for a plane from the previous slide, we get this equation. So this is the equation for the tangent plane. At this point over here, there's a red dot showing you where that is. Just like in calculus, you had second derivatives. We have second derivatives, and we could have third derivatives and fourth derivatives, but let's just stick with second derivatives. The thing is, we've got x's and y's floating around, so we've got different ways of doing this. And we have other notation. Remember how you had y prime for the derivative, but you also had dy dx, and you had all this other kind of stuff? Same thing is true here, and it gets more complicated. So the partial with respect to x can be written either as f sub x, or that funky symbol, which we call partial of f with respect to x. Or we could also say partial of z with respect to x. Similarly, if I want to take the second derivative with respect to x, I could say f sub x. And using that funky 6 symbol, I have the partial with respect to x of the partial of f with respect to x. Keep in mind, doing the partial is a function. So we already took the partial of f with respect to x once, and then we're going to compose it and do it again with another partial with respect to x. This is kind of clunky. A shorthand we can use is, say, partial squared of f over partial x squared. What if I take the derivative with respect to x and then take it with respect to y? Well, that means we have the partial of f with respect to x, but then we hit it on the outside with the partial with respect to y. And if I write it with the square notation, you get something like this. And notice the order here. I have partial of y, partial of x, because that's the order. X went first, and then y. We write it backward, just like you do with composition notation. But wait, there's more. What if you want to do the partial with respect to y twice? Same idea as with the partial with respect to x twice. Or you could do the partial of y and then the partial of x. So you get something like this. Yeah, there's a whole bunch of partials. And what about if I do the partial of x and then y and then x again, or x, y? There's all kinds of things we can do. Let's look at an example. Let's go back to our previous one. I have got x squared y minus 3y to the fourth. I already know that the partial with respect to x is 2xy. The partial with respect to x again, well, I take this expression, 2xy. If I'm taking that with respect to x, 2 and y are treated as constants, so the partial with respect to x again is 2y. I can do f sub xy, taking the derivative of f sub x with respect to y, and now 2x is treated as a constant. I get 2x. I'm getting really tongue-tied doing this. There is good news, though. If f is defined on a disk D that contains the point AB, and fxy and fyx are continuous on D, then the partial xy is the same as the partial yx. In other words, order doesn't matter, as long as everything's pretty. So let's look at that example again. I have x squared y minus 3y to the fourth. The partial with respect to x is 2xy. The partial with respect to y is x squared minus 12y cubed. Now if I take f sub x and take the derivative with respect to y, we already know we're going to get 2x. Looking at f sub y, if I take the derivative of this with respect to x, this 12y cubed goes away, and I'm left with, you got it, 2x. or it doesn't matter for second derivatives if you've got a nice pretty function. So the key is you're going to want to choose wisely which one you take the derivative of first. So now we know how to find the partial with respect to x and with respect to y. We can find second partials with respect to x's and y's, and we can use that information to find the equation for the tangent plane at a point. Next, we want to figure out where this surface will have a high point or a low point, but that's for another video.